In the previous video, we looked at the various Matlab functions for making special purpose plots, log plots, semi-log plots, stairs plots, stem plots, bar plots, pie plots, that kind of thing, right? And in this video, we're going to talk about various ways for graph enhancements. Where's my cursor? So what I'm going to do is for graph enhancements. Graph enhancements. Graph enhancements. Right. So graph enhancements including various things, for example, labels, the title, if we want to add mixed text explanations with the graph together, that kind of thing, right? So let's look at how we can actually do that kind of thing. So we're going to do labels, title, and text placements first. So what we're going to do is that we're going to draw a plot with two curves, two intersecting curves on it, right? So let's create some fake data first. X equals to link space 0 to 6 with like 1,000 points or something. Doesn't matter. Right? Or maybe 100 points just to speed up the. And then we can we're going to try to plot two functions. One is cosine x. The other one is so y is going to equal to cosine of x, and then y1 is going to equal to 1 dot divide cosh. It's a transcendental function x, right? If you haven't used this particular function before, you can look it up, right, by typing help cosh, right? And then we're going to create a new figure that's called figure 5, right? But this time we're not going to make any subplots because subplots are kind of small, so it's kind of difficult to actually look at those different kind of enhancements, right? So we're just going to do a plot x, y. That's going to be our first curve, and then that's going to be in black line, and then x, y1, that's also going to be black, right? Right. So if we just plot that, if we just execute this code, this piece of code, we're going to see the two lines, right? So this line is kind of obvious, right? That's the cosine function. That's y, right? That's y. And then this line is actually the cosh 1 divided by cosh x, y1. This line, that's this line. And you can sort of see these two lines are actually intersecting at this particular point. Right. Now suppose we want to put a vertical bar. We want to put a vertical line across this particular intersection point, right? How do we actually do that, right? If I tell you the horizontal axis of this intersection point is 4.73, right? How do we actually make a plot the vertical line? Plot the vertical line, right? So let's add one more line onto it. The horizontal. So again, the vertical line can be specified just by using 2 points. We can just use 2 points. 1 point located here, 1 point located here, right? And both points is going to have a horizontal axis that's 4.73, and then the vertical axis is going to be -1 for the first point, and then +1 for the second point, right? So it's going to be 4.73. 4.73. That's the horizontal axis of the 2 points, right? And then the vertical axis is going to be -1, 1, right? And then we're also going to use k, right? So now we've got like 3 lines intersecting at the same point. First, let's look at how to use the X label, right? We have used the X label before, but right, X label X. If we just do that, then it's gonna. For now, the figure doesn't have an X label, right? You don't see any label here down here, right? But if I execute this line, you're gonna see X appear here. See, right? And if you want to sort of increase the font size, the X label actually takes an option that's called a font size, right? Let's give it like 14 or something, right? So we're gonna make the font slightly bigger. right? That's making the font slightly bigger. And of course, you also have y label. Y label, value of functions. Let's just call it value of functions. If you can see TIO, right? And then again, font size is going to be, let's call it 14 or something, right? So value of functions, that's going to be a y label. And now let's try to put some text onto this particular plot. Let's try to put some text onto this particular plot, right? So what we want to do is to actually put text cosine x and 1 divided by cos hx on near these two black curves, right? And then we want to put a text x equals to 4.73 sort of at the location that's close to this particular intersection, right? So how can we actually do that? The Matlab text function allows us to do that, right? It's called a text. If you haven't used it before, we can just take a look at the manual page for text function. Okay, help text. Right. So it's xy_str. So adds a text description that's inside of the str, this particular string, to one or more data points in the current access using the text specified by str, right? So to add text to one point, specify x and y as scalars in data units, right? So let's just try out this text function, right? Suppose we want to add suppose we want to add the x equals to 4.73. This particular text string x equals to 4.73. We want to add this particular text string to a location that's at x equals to 4.8 and y equals to minus 0.1. Right. Let's execute this line of code. So now you can sort of see this particular piece of code, particular text that's located at this particular location, right? So x equals to 4.8, that's slightly to the right of this vertical line, right? And then y equals to minus 0.1, that's about at this particular location. So the text is going to start, the text string is going to start at the coordinates that you specify here. You see how this thing works, right? Let me see if it actually takes font size. Right, let me give it a try. I don't really know actually, so evaluate. So it looks like it's gonna take a font size, right? That makes the font bigger, but for some reason it's actually. So let me remake this particular figure. Let me just Control Enter. Right. That's x equals to 4.73. Okay. And then if we want to add the name of the function or the form of the functions on close to the curves, let's use text again, right? Say 2.1, that's going to be the starting location, the coordinate of the string 1 divided by cos hx, right? So this thing is going to be the string that we're going to display, right? Where are we going to display it? We're going to display it at the coordinate x equals to 2.1 and y equals to 0.3, right? Suppose we execute this thing. Let me add a font size. Right, 1 divided by cosine cos hx. So that's this particular curve, right? And then let's add one more text. This time it's not 2.1 anymore, it's 1.2 minus 0.4. And then the string we want to display is cos parenthesis x, and then font size 14. So that's COSX, right? Maybe it's kind of too far away from the curve. It's 1.2. It's probably 1.8, 1.7. That might be better. Right? 1 point. Yeah, that might be better, right? So let me remake the figure. Oh, 1.6 might be better. Yeah, that gives us a better looking figure, right? And then the last thing that I want to do is to add a title to the top of the figure. And that can be done by using the title function, right? So let's just call it visualization of two intersecting curves. Right. And that's going to be our title. And again, let's change the font size, like 14. So now it's got a title on top of it, visualization of two intersecting curves, right? So those are some of the basic usages of labels, titles, and the text. How to actually mix them together with the curves, right? And the second thing about graph enhancement is called legend, right? Legend. Let's create another figure. Let's call it figure 6. So how do we actually use legends, right? But again, let's let's copy some piece of the codes, X label, Y label, and we're gonna do this particular text. Copy it over, right? Um, let's also copy over the title, and then let's put the title after the Y label, right? But this time we're not gonna sort of plot the text to draw the text of the function form on the together with the curves. Instead, we're gonna use legends, right? We're gonna use legends. So in order to use legend, we can use the MATLAB function called legend, right? And then legend is gonna take strings as inputs, and the number of strings is going to depend upon how many curves we're actually plotting. So here we're actually plotting 2 curves, right? In fact, it's actually 3 curves, but the last curve is just for the last vertical line is just for indicating where the intersection actually is located, right? What we care about is just the first 2 curves, right? So in this case, all we have to do is to specify the strings for the first 2 curves, right? So the first curve is going to be cosine of x, right? That's the string to indicate the form of the function. And then the second one is 1 divided by coshx, right? So if we just do that, let's just run this piece of code. Then we're going to see this thing, right? So, but again, this is a bad example, right? Because the 2 curves are plotted in exactly the same style, black solid line, right? That's not exactly what we wanted, right? What we wanted is to actually use different line styles. So let's change them. Let's use dash line for the second curve, right? And then re-execute this particular portion of the code. So that's better, right? That's better. So the solid line, black solid line, is going to be cosine x, and then the 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 the, the black dashed line is going to be 1 over cosine cos hx, right? And then by default, the legend box, you can sort of see the legend box here, is going to be located on the upper right corner of the plot, right? Suppose you want to move the box here. One of the ways is just to drag them, right? You can drag them. But if you want to sort of do this kind of thing programmatically, you can give it another option. Let's give it a southwest, right? And then if you execute this piece of code, that's gonna give you, oh, so it's a location southwest. You have to sort of, so if you just specify southwest, it's gonna use it as a string for the third curve, because you actually have a third curve, right? You have to sort of specify the key value pair. The key is location, right? And then the value is southwest, right? Sorry about that. Let me reevaluate this particular section of the code. Right. So now the legend box is right here. Right. Sometimes you might want to get rid of the box that's surrounding the text, right? So this box looks kind of some people like it, some people don't like it, right? So if your preference is actually to get rid of the outside bounding box of the legend, you've got another option that's called legend box off, right? And then if you reevaluate this section of the code, you're gonna get the legend box without the solid line outline, the solid black outline, right? And that's some kind of a that's how we can actually use the legends. Now suppose we wanna, so this is a pretty good looking figure already, right? But suppose we wanna sort of emphasize some of the special regions on this particular plot, right? One of those regions is probably just between these two lines in this particular region, right? The area that's enclosed by these two curves, right? This particular area, right? This particular area. So suppose we want to fill up this particular region with a specific color, say red color. So how can we actually do that, right? So Matlab provides a function that's called a fill. So it's got a function that's called a fill. Filling regions. So if you haven't used the fill function before, you can type help fill, right? So x, y, c. C is basically the color for the region, and x, y is some kind of 2D polygon defined by the vector x and y, right? So how do we actually specify this polygon, right? So it's actually easier than you think, because we know the specific form of this particular these two curves, right? So what we have to do is to actually specify this portion of the curve first, the solid black line, right? From 0 to 4.73, right? And then all we have to do is to specify the next portion that's indicated by this dash black curve, right? That goes from like 4.73 back to 0, right? So if we can actually specify these two segments, then we got a complete curve, complete sort of a bounding curve, right? So how do we actually construct these two curves, right? It's slightly tricky. So let's create the horizontal axis first. Xn, let's call it xn. Xn is different from x, right? X goes from like 0 to 6, right? But for xn, all we want to do is to actually go from link space, so from 0 to like 4.73, and then with like 50 points or something, right? Right. And then we don't want to sort of plot on top of this figure 6. We don't want to sort of erase all the curves and all the legends that we have already created. Let's hold on. Let's hold on to the previous plot. And then we can just call the fill function. So how are we going to specify this bounding box, this bounding curves, right? So let's specify this part of the curve first. Let's specify the bounding curve that goes from x equal to 0 to 4.73 for this black solid curve, right? We're gonna go this way. We're gonna go this way, right? So it's gonna be xn, right? So xn goes from 0 to 4.73, right? And then the horizontal axis for this black dash line, even though it also goes from 0 to 4.73, right? But in order to actually specify a closed curve, a closed boundary, we cannot go from 0 to 4.73. We have to go from 4.73 back to 0. So, which means that we're starting from this location, right, to go down along this particular black solid curve, right? And then once we reach x equal to 4.73, we go back along this black dash curve, right? So, which means that we have to go from x equals 4.73 back to 0. So, how do we actually specify that? It's actually quite easy. Just use the flip left right xn with xn as input, right? So that's going to give us a vector that goes from 4.73 back to 0, right? So that's going to be the horizontal axis. So don't forget xn is actually a row vector, right? So this is a row vector, this is another row vector, right? But we are concatenating these two row vectors with just a comma, which means what? Which means that this particular large vector is also a row vector, but its length is like a double of the length of xn, right? And so horizontal axis is going to go from 0 to 4.73 and then back from 4.73 back to 0, right? So it's going to go this way and then back, right? And then what's going to be the corresponding y-axis, right? What's going to be the corresponding y-axis, right? Um, so let's for this particular segment, that's relatively easy, right? That's cosine x, right? Cosine x xn, right? And then for the segment that goes back, that's like a 1, that's 1 divided by 1 dot divide cosh xn, right? But don't forget, we have to flip it, right? And then we use red color, right? Let's give it a run and see if we are successful. Yeah, we're indeed successful, right? So we have actually filled up this particular region with red color, right? So this kind of feeling, or this kind of a region feeling, or filling up a region with a specific color, is actually quite a useful technique for emphasizing specific features in your graph, right? So let's try to explore it a little bit more, and by trying to um, create a new figure, right? So this time we're gonna investigate overlapping filling regions. Right? So again, let's try to create some fake data link space. So 0 to like 2 times pi with 100 points, right? And then let's do a figure 7. And then subplot 1 row 2 column first. And then in this particular region, we're going to do a fill. In this particular subplot, we're going to do a fill t. That's the horizontal axis, right? And then 0.5 times sine of 2 times t. And then we're going to use yellow. Y means yellow, right? And then let's execute this portion of the code. Oh, for some reason I always make this kind of the same mistake. right? So that's gonna give us this kind of field, yellow field, right? So how it's gonna feel it, right? The horizontal axis is gonna be t, right? T goes from like 0 to 2 pi, and then the vertical axis is gonna be 0.5 times sine 2t. So the amplitude is like goes from like minus 0.5 to 0.5, right? And that's sort of the effect of this particular field command or field function call, right? Um, so on this particular plot, you can sort of see there's some white space that's not utilized, right? So if you want to get rid of those all those unutilized white space, there's a quite a convenient command that's called access tight, right? If you do access tight, then the bounding box is going to be tight around the content of the figure, right? Right. And then on top of this particular figure, let's do a hold on, and then do another field, but this time it's going to be t sine t, right? And then with red color, with red color. Did I do it? Hold on. I did hold on, right? Yeah, I did hold on. But why can't I see the yellow curve, yellow field anymore? That looks like it's is that supposed to happen? Uh, I did say hold on, right? I did say hold on, right? And then okay, so that looks like it's I didn't actually do it right. I didn't actually do it right. Let me go back to adjust my codes. Right. So uh, let me cut this code. Then paste it. Right. Let me see if I can get this thing to work now. Right. So now it looks like it's working now. Right. So you can sort of see the red color field regions is right on top of those yellow color field regions, right? And some of the portions, some of the yellow color are being covered by the red color, right? So that's overlapping field regions, right? So if that's what you wanted, then that would be good, right? That would be good, right? But if that's not exactly what you wanted, you have to be careful about which plot you want to put on top and which plot you want to put on bottom, right? So subplot one row, two column in the second one, and then this time we're gonna do this field first, right? And then hold on, and then do the next field, and then access tight, right? Right. So this time we can see both the yellow field, color field, and then the red color field. But again, yellow color field is gonna cover portions of the red color field, right? So you can guess what's actually happening behind the yellow uh, patch, right? But you don't really know for sure, right? Because it's covered. Um, so how do we actually solve this kind of a issue, right? So this kind of overlapping color field sometimes can hide information that you don't really wanna you want to expose, right? So let's look at another capability that's called transparency, right? So Matlab actually provides the capability to actually fill up a region with some level of transparency, right? Um, let's recreate another figure. Let's create figure 8. Let's create a figure 8, and then again subplot one row, two column, the first one, and then fill t 0.5 times sine of 2 times t, and then let's just use yellow, right? And then hold on, and then fill t sine of t, but this time with red color. But how do we actually specify the transparency, right? There are two properties that we need to adjust. The first property has a name called face vertex alpha data. Let's give it 0.6, and then face alpha flat, and then access tight. Right. So let's just run it and let's see what's actually going to be the effect. So you can sort of see it's not exactly pure red, right? It's got some kind of pinkish red. The reason that you see this kind of deviation from pure red is because there's some kind of transparency that's associated with it. And then this time you can sort of see the yellow field in the background, right? But again, it's not pure yellow, right? Because it's actually yellow mixed with the front red color with some kind of level of transparency. So it looks like orange, right? But that's sort of the effect of transparency, right? And in order to actually specify transparency, you have to sort of do these two options. One is called face vertex alpha data, which means what? Which means that you're going to assign those alpha data. Alpha means transparency. So 0 means completely transparent. You won't be able to see anything, right? You're going to see through it, right? And then 1 means completely opaque. So it's going to completely block the background, right? And any value that's between 0 and 1, for example 0.6 here, gives us some level of transparency, right? So you will be able to see the background, right? But you won't be able to see the background exactly because it's just a translucent, right? So you're assigning this kind of alpha value to all the face vertex, right? So face vertex alpha data. Vertex means points, right? So every patch got lots of boundaries, right? Every patch, every color patch has boundaries, and on those boundaries are actually vertices, those face vertex. And then you're going to assign this kind of 0.6 alpha data, the transparency data, to those vertices. And then face alpha flat means what? Means you're going to assign those alpha data to all the interior patch, to the interior of the patch also. So all the interior of the patch are also going to have a value of 0.6, right? Alpha value of 0.6. So that's what this command is actually. How to use the transparency, right? But let's try a different transparency value, right? So subplot one row, two column, the second one, and then fill. Let me just copy this over. Instead of 0.6, let's change it to 1. So let's just run this part of the code. So for some reason it's not exactly working as what I was expecting for some reason. Right. Maybe I should change it to 0 and see what's going to happen. Right, I probably should have used 0 instead of 1, right? 1 is still going to be transparent, but 0 is not going to be transparent. It's going to give you this kind of solid color, right? So by changing it to 0, so alpha equals, so what I was saying is wrong, right? It's just the opposite. So 0 means no transparency, right? Instead of 1. Right. So what I was saying is that 1 means transparency, but actually, in fact, it's actually the opposite. 0 actually means completely 0 means no transparent, completely opaque, right? Okay, that's transparency, right? Transparency. And then the last thing that I want to show you is the so-called patch, right? So for now we have seen some utilities of the patch, the color patches, right? If you fill a certain region with color, that's called a patch, right? But let's look at the patch in a more specific example, right? So this time we're going to try to draw some rectangles. We're going to try to draw some rectangles, right? Every rectangle has like a 4 corners, right? But in order to actually draw a rectangle, we actually need like a uh, uh, 5 points because we want to close the last segment, right? So let's try to specify the coordinates, the x coordinate of the first rectangle. Let's just call it x1. It's gonna start from 0 and then 0, then 1, 1, 0, right? That's gonna be the x coordinate. Y coordinate is gonna equal to also 0 and then 1, 1, 0, 0, right? Um, so the first point, the location of the first point is exactly the same as the location of the last point, which means that we're drawing a closed curve, right? So that's the first rectangle. And then let's try to do the second rectangle. The horizontal axis is going to equal to 0.5, 0.5, 2.0, 2.0, 0.5. That's going to be the horizontal axis. Y2 is going to equal to 0.5, 2.0, 2.0, 0.5, 0.5. Right. And then let's try to create another figure that's called figure 9. Figure 9. And this time we're going to just use patch, the patch command. So let's just draw a patch. Right. So x1, y1, and then we're going to use yellow. And then we can specify the edge color. We specify the edge color to be blue, the line width to be 2.5, the face vertex arva data, let's give it a 0.6, and then face arva flat. Right, that's gonna be how we are gonna draw the first rectangle. Let's just run this part of the code. So that's our first rectangle, right? It's got blue edges, right? And then the color is gonna be yellow, right? It's gonna be yellow interior. The rectangle is supposed to be look like a square, right? Because the length is going to be exactly 1 in each dimension. But for some reason, but if you actually plot this in the default graphic window, it's going to look like a rectangle, right? The reason is because the horizontal and the vertical axis has different scale, right? So you can sort of see on the vertical axis, 0.1 looks like this long, but on the horizontal axis, 0.1 looks like a lot longer, right? So if you want to sort of correct this kind of behavior, there's another command that's called axis equal, and if you call this particular command, that's going to give you the if you use this particular command, that's going to give you this thing. It's going to force the horizontal and vertical axis to be have the same scale, so that a square looks like a square instead of a kind of elongated rectangle, right? But that's just the first square, right? That's the first square. But let's plot the second square, x2, y2, green, and then edge color is going to be red, and then line width is going to be 3.5, right? Let's Let's execute this particular line of code. So now you can sort of see two squares, right? Um, but we are not really seeing the because the green square doesn't have transparency, right? It's the yellow square that has transparency. So maybe I should actually plot. Uh, maybe I should have plot. Let me just cut this piece of the code and then copy it over here. Right. And then let's run this piece of code. For some reason, it's still not working. Why? I still have some problem with the with Arvo, right? Let me turn off the access. Not enough input arguments. Oh, oh, I see. That's because line width. I sort of removed the line width for some reason. 2.5, right? Maybe I should just close this one and then remake another one. Yeah, so this time it looks like it's better, right? I turned off the access, so we won't be able to see the white background. It's just the gray background without the white background, right? And then access equal, and then access off. Right, so now squares look like squares, and then you have some transparency on the green square, so you can see the background yellow square, right? And then by default patch is going to be hold on, right? So the new patch is not going to overwrite, or is not going to erase the old patch, right? The new patch is not going to overwrite the old patch, so it's going to give you the correct. It's gonna give you a overlay plot by default, right? And it's gonna look like that. So that's how we can actually use patches, right? The last thing that we want to talk about is how do we actually include mathematical symbols, or how do we actually include those Greek letters, that kind of thing, into our plots, and then how we can actually use some more advanced uses of graphic handles, right? Graphic handles. But maybe we'll talk about that in the next video.